Hi, everyone. So we're here for the next lesson in Unit 3, and it's called the empirical formula. And what the empirical formula is, quite simply, is it's the simplest it's called the simplest formula of a compound. It's called the simplest formula. And really, what it is it's the smallest whole number ratio in which the atoms combine. Okay, and I want to emphasize here that it's got to be a whole number, and so we're going to see that plays a role as we investigate these. Now, one thing I want to start off with is just making sure that you understand that the way in which atoms combine into molecules is based on electron, the electron arrangement and the electron sharing or transfer that we discussed in Unit 1, and that hasn't changed. But what we're going to be doing in this unit is trying to understand, based on mass information, can we deduce the empirical formula? And in the next lesson, can we deduce the molecular formula? So I just want to emphasize that nothing has changed from Unit 1. If you wanted to investigate the formula or why atoms combine in certain ways, you would always be looking at electrons and electron arrangements. Now, we're not interested in that in this unit because we're more interested in it from a quantitative standpoint and being given mass information like the percent mass of each element in a compound. So one thing that just to distinguish here, and we're going to be talking about this more in the next lesson, is we want to just, I'm going to put here versus, so this lesson is all about the empirical formula or the simplest formula, but just to kind of contrast it to the molecular formula. And the molecular formula is the one that you're most familiar with. The molecular formula is the one that we were dealing with in Unit 1. And the molecular formula is the actual number of atoms in a compound. Sorry, I'm just going to clean that up. Of atoms in a compound. So I'm gonna go over some examples here in a second, but essentially this is the one that that you would most closely associate with with what you've learned about molecules. So example, if I were to ask you for the molecular formula of water, you would say to me it's H2O. Okay, so that's the formula that we've been most familiar with. In today's lesson, we're going to talk about this idea of the empirical formula. Okay, well, I've created a little table here on this next page. And so just to kind of help you to understand what this empirical formula is, well, let's start off with an easy one. And let's say we have carbon dioxide. Well, you guys know that you would write its molecular formula as CO2, a carbon and 2 oxygens. Now, the empirical formula of a compound is the simplest whole number ratio. So really, you may say, well, what does that mean in this case? Because in this case, there's 1 carbon and 2 oxygens. And so guess what? In this particular example, carbon dioxide is also the simplest, CO2, sorry, is also the simplest formula, or the empirical formula, because that is the smallest whole number ratio. And so the multiplier, in other words, how you would go from the empirical formula to the molecular formula, is you would multiply all of your subscripts by 1. Well, let's look at another one maybe that might help to, I think maybe you're probably still a little bit confused about this. So I'm going to give you the molecular formula of butane. So this is what you use in lighters. And the molecular formula is C4H10. So there are 4 carbons and 10 hydrogens in butane. Well, in this particular case, there is a smaller or simpler formula. In other words, we can see that 2 goes evenly into both of those numbers. And so technically, the empirical formula of butane is C2H5, okay? Because it's the smallest whole number ratio. So the smallest ratio is 2 to 5 versus 4 to 10. And the multiplier is times 2. In other words, to go from the empirical formula to the molecular formula, you would double everything. All right, let's look at another one. Benzene is C6H6. And so the smallest whole number ratio would be CH, or C1H1, because 6 goes evenly, obviously, into both of those. And so the multiplier between them is 6. Okay, potassium sulfate. You could also have empirical formulas for ionic compounds. And I wanted to emphasize that here. These ones, the first 3 I've done are covalent compounds or molecular, but you can also have it for ionic. And so here, potassium sulfate is K2SO4. And so what is the smallest whole number ratio there? Well, the smallest number that goes evenly into 2, 1, because there's a 1 with sulfur, and 4 is just the 1. So again, this one, its empirical formula is the same as its molecular formula. So it's just K2SO4, and so its multiplier is 1. But here's an example of one that is potassium oxalate. Can be written as the following. It's K2 and then C2O4. Oxalate is a polyatomic ion, and so it is C2O4. But you can see that its smallest or empirical formula, 2 goes evenly into all those, so its smallest would be KCO2. And its multiplier is 2. So the smallest or the empirical formula is just written, all of the subscripts written in the lowest form that they can go. A couple of quick questions is, can more than one compound have the same empirical formula? Can more than one compound have the same empirical formula? Have the same, sorry for that noise in the background, have the same empirical formula? And the answer to that is yes. I'll give you an example. I'm going to put another one on the bottom here. We have a substance called acetylene, and sorry, I've misspelled that. Here we go. Acetylene is used in welding, and so acetylene, and that's the common name for it, but acetylene is C2H2, so it would have an empirical formula of CH and have a multiplier of 2. So look at this, benzene and acetylene actually share the same empirical formula. Now, it's important to note that they have very unique molecular formulas, and so that's fine. We can see that that's the case. But so yes, in answer to that question, they can have more than one compound can have the same empirical formula. And can a compound have the same empirical formula, and I'm just going to do EF for short, and molecular formula. I'll do MF for short. Can a compound have the same empirical molecular formula? And obviously the answer there is yes as well, because we saw that in a few different examples. We saw that with CO2. We saw that with potassium sulfate. So in those cases, they had the same empirical and molecular formula. Okay. Next, I'd like to walk you through some empirical formula problems. So basically, these are the steps you're going to go through to find the empirical formula based on the percent composition that you've been given. And this is, it's very applicable, is that in many situations, you'll be able to gather data about the percent of the different elements present in a compound. And the goal then is to be able to say, well, if that's the percent present, I know the empirical formula. So your goal is to develop the empirical formula based on the percent composition. And the example we're going to walk through here is you've just been told that a certain compound has 14.87% phosphorus and 85.13% chlorine. And you want to know what the empirical formula is. Okay, so here we go. We're going to do that example as I show you these steps. So step number one is to convert to grams. And basically, given your percent composition, assume that you had 100 grams. So watch this. Given that, and I'm going to put a P here for phosphorus, that I would have, if I had 100 grams of it, I would have 14.87 grams of phosphorus. Obviously, if it's 14.87% phosphorus, then I would have my 100 grams would be made up of 14.87 grams of of phosphorus and 85.13 grams of chlorine. And so really all I'm doing is turning my percent into the grams. So that's step number one. Step number two is to convert from grams to moles. Basically, here's the thing, is that an empirical formula is a count of the atoms within the formula. It's a count. And so I've got to change my mass into a count. And we do that using our little conversion where n is equal to little m over big M. And so for the first one, it's equal to my sample mass of phosphorus is 14.87. Okay, I look up on my periodic table and my molar mass of phosphorus is 30.97 grams per mole. And so when I do that calculation, I get 0.480 moles. Okay, and when I do that for chlorine, I take my sample mass, which is 85.13. That's the mass that was in the substance. I divide it by the molar mass. I look it up on the periodic table, and it's 35.45. And when I do that math, I get 2.401 moles. So these are both, the unit there is mole and mole. And remember, that's a count. It's like 0.48 dozen. But in this case, it's 0.48 moles. So I've turned a mass into a count. Step three is to divide the smallest number of moles by all the others. You're going to get a ratio of the smallest element to the remaining elements. So I only have two here. So basically the ratio, so the smallest number is the 0.48 moles. And so I'm going to divide. In this case, for the first one, it's kind of easy. It's 0.48 divided by 0.48, so that's 1. And for the other one, I take the 2.401 and I divide it by the smallest, so it's 0.480, and I get a number of 5.002. Now, here we go. So we're almost done. Basically, a couple of key points. if you're within 0.05 of a number, you can round. But if you're not, you cannot. So look at this. My final answer here for phosphorus is 1. Obviously, there was no rounding necessary. And here, because this one was 5.002, I'm within 0.05, so I can round it to 5. And so therefore, I know the empirical formula is P1Cl5. That is the simplest formula. Now again, I don't know what the molecular formula is, because remember, it could technically be any whole number multiple of that. So it could be P2Cl10 or P3Cl15. But at this point, what I do know for a fact is that its simplest formula is PCl5. Now, I just wanted to revisit these last 2 points here. Okay, these last 2 points with an example of where you may have to do something extra in step 3. So you may not be within 0.05 of a whole number. And let's look at this. I've given you this table that your textbook gives you. Let's say that you were doing your analysis, and in step 2, you got your answers were 3 moles. You had 6 moles, and you had 2 moles. This is step 2. You got those answers. So you got 3 moles, 6 moles, and 2 moles. And then in step 3, when you went to divide them by the smallest, well, you would divide this by 2, you divide this by 2, and divide this by 2. You divide by the smallest. And so here you end up with 1.5, here you end up with 3, and here you end up with 1. And so you're at this point where, and I'm going to say, we'll put some elements in here. We'll say that was carbon, that was hydrogen, and that was oxygen. And so now you're going to write your empirical formula, but unfortunately you can't round the 1.5. It's not within 0.05 of a number. You can't round it to 2 because it's too far away from 2. So what you do is you look at this table to your left here and use that to get it closer to a whole number. So watch this. I'm going to show you right here. In this particular, if your decimal is 0.5, you would multiply it by 2, but you've got to multiply everything by 2. So look at this. You would do 2 times all of these numbers, and that gives you here 3, 6, and 2. And so your empirical formula is C3H6O2. Okay, so that's what they mean. Let me give you another example of that. Let's say that you had here, when you did step 2, you ended up with the following moles. Let's say you ended up with 1 and 3.67. Okay, so at the end of once you've looked at those and you go, well, I can't round this to 4. And so you'd look at your table and you'd go, oh, wait, okay, so I'm going to multiply everything by 3. So you would do 3 times everything, and you get 3, and you get 11. So that gives you whole numbers. Let's say it had been something like S3P11. So, just be aware that in step 2 and 3, as you're doing those calculations, you may end up with a number that doesn't allow you to round. Like a lot of you may think, well, I should just round that one to 4, but you cannot in this case. In the empirical formula steps, you can't do that. You need to use this table to try to get closer to a whole number. Okay, so you're going to go ahead and try some of these homework questions. I show them here, number 10 and 12 on page 209, and then 14 and 16 on 209. And then here are some section review questions that I'd like you to try as well. And I've listed the answers here. You can see that you can double check that you're getting the right empirical formula. Good luck.